Hey guys, I know for the last 5 videos, we've been going one chapter at a time. I was planning to do the same, however, chapters 6 through 8 are all basically about the same thing and they're so deeply related that I kind of have to put them together. So we'll be crunching 3 chapters into one video today. So before we've talked about one variable representation. So if we went around and surveyed some students for their heights, we have one set of data, which is their heights. Now we're starting to get into 2 variable statistics. So that's when we ask kids their heights and their ages. So now we have 2 sets of data and we're putting them together in a scatter plot. So there's some main terms that you need to know before we get started. And we'll start with your explanatory variable and your response variable. In the past, you've likely dealt with different words for the same things, which are the dependent variable and the independent variable. So that's essentially what we're doing here. Our dependent variable, so our y variable, has now become the response variable, and our independent variable, which is the x variable, has become the explanatory variable. So coming over to this scatter plot, our explanatory variable would be the average temperature, and then our response variable would be the daily sales. Finally, we have our line of best fit, which is probably what you're used to calling it. In statistics, we have a different name for it. We call it the LSRL, which is short, least squares regression line. This is basically the line that you put through your scatter plot that best describes the trend of the data. So that is what this red line over here is. So a lot of what you'll have to do is making scatter plots off of data sets. So this is what I've done here. I've taken this table and I've converted it into a scatter plot. See, mine's pretty messy, but it has the general elements that you need. The first is a title, y-axis label, and then your x-axis label. The axes all have scale marks. And then, although it doesn't have a line of best fit, it is not necessary, but I have plotted all 7 data points, I believe. So before we've had to cuss to describe the distribution of one variable statistics. So we took a histogram and then we used cuss to describe what the shape of the chart looks like. We have to do the same thing with scatter plots, but now instead of using cuss, we're using a different acronym called FUDS, F-U-D-S. And so there are 4 things we need to describe. The first one is form. Is the form of the scatter plot linear or nonlinear? Do the dots look like they're following some sort of line? If there's some curves or weird bends to it, then it's nonlinear. You don't have to specifically say if it's parabolic looking or exponential looking, because this course is a linear statistics course, so it's fine to just say linear or nonlinear. For unusual features, this is very similar to the U in cuss. It's asking about outliers, or this new element, which is if there's any clustering in the data. So what that would look like is if you had a plot and then all of the data points are really thick over here, but then they're all lighter over here in terms of how thick they are. So this would be a major cluster, and this is an unusual feature that you need to point out. Next we have direction. So you would say it's positive or negative. So are the data points moving in an upwards direction like you can see here? Or are they moving downwards as x increases? So does it look like this? Ooh, that is a terrible plot. That is a strong negative association. So speaking of which, our S in FUDS is for strength. So is there a strong, moderate, or weak association between the x and y variables? What this means is how clear is our line that the dots are making? So if all of the points are packed together in some definite form, then that is a strong association. For a moderate association, we would see something a little bit more spread out, but you can definitely see that there is a trend to the data. Then for a weak association, it's kind of hard to tell what kind of shape it's making. There might be an association if you actually put it into the calculator and check, but it's very difficult to tell. So there is a way to tell the strength without just eyeballing it, which is using a number called R. So R is the correlation coefficient, is what it's called, and it tells you the strength and the direction of an association between 2 variables. So some properties of R is that it is always between -1 and 1. So if we have an R value of 0.9, there are a couple things we need to notice. First, we notice that it is positive. So if the R value is positive, that means that the association is positive. So the data points are moving upwards as x increases. Then the 0.9. You can see that 0.9 is very, very close to 1, so that tells you that the association is very strong. Instead of positive 0.9, if we had negative 0.9 instead, what would change? So we notice that this is negative now. That means the association is also negative. So our scatter plot points are moving downwards as x increases. But the 0.9 still means that the association is very strong. So don't be tricked and think that just because the R value is negative, that the association is weak. As long as it is close to either 1 or -1, then it is very strong. So the best way to think about this is to think about absolute value. So if the absolute value of the R value is close to 1, that means there is a strong association. Generally, when you're telling strength based off of R values, the rule is that if it's between 0.7 and 0.9, then it's a strong association. If it's between 0.55-ish and 0.7, then it would be moderate. And if it's between 0 and 0.55, it is a weak association. And to account for the negative R values, just put in absolute values. So a lot of the times you'll get questions that ask you to interpret the R value. So what you have to say is, first, you have to name what the R value is. So earlier we were talking with -0.9, so we'll put that in. The R value of -0.9 implies a strong negative association between the explanatory and response variable. So I left this at explanatory and response variable, but when you actually answer questions, you need to put in the context. So if this were between age and memory, then we would say the value of -0.9 implies a strong negative association between age and memory. So there's one thing that you really need to pay attention to, which is this word association here. You've probably heard this before, that correlation does not mean causation, and that's essentially what this association is doing. So when we say association, that means that there appears to be some kind of relationship. However, this is not something about causation, which is why we're not using the word correlation here, we're just using association. The variables appear to be related, but we can't be sure. And that is also why we use the word implies here. This R value does not prove anything, but it is a good indicator of whether or not there is a relationship. So one more thing about the R value is that the R value is only applicable for linear models. So the R value will tell you how strong your linear association is, but if you have a really strong association that is nonlinear, like if we have a parabola looking thing here, if you just look at it, you can tell that there is a very strong relationship here. It almost falls perfectly into a parabolic shape. However, if we plugged all the points into a calculator and got the R value, it would be around 0, because the R value only measures a linear association. It doesn't do anything to account for this curved shape here. There is another thing that we can do with the R value, which is square it. So once we square it, we get a new name for it, which is the coefficient of determination. And what it tells us is how good our model is. So how much variation in data does our line of best fit account for? So it essentially tells us what percentage of the variation in the points is explained by our model, which, when I say model, that is pointing to our LSRL, or line of best fit. So it just tells us how good did we do? How well does the model fit the data set? And when asked to interpret the coefficient of determination, you would say something along the lines of the R-squared value of, let's say, 0.81 tells us that 81% of the variation in, let's say, memory can be explained by variation in age. So there's more special properties of scatterplots. One special property you need to remember is that the R will not change if you flip the X and the Y axis. So before, if we have a plot like this, we have x, y, and then we have something like this. If we put our x as our y-axis and our y as our x-axis, so we just flip the scatter plot over, our r value will not change. Another thing is that the r value is unitless. The r value is derived from z-scores and both are therefore unitless. R values are also not affected by changes to center or scale. So if you added 5 to every single data point in your scatter plot, or if we moved it to the side, so if we took the scatter plot and changed it into something like this, the r value would still remain the same. Similarly, if we multiplied every data point by 10, r value will not change. The r value is also very sensitive to outliers, so if you have this scatter plot and then a point way out here, the r value will likely be lowered by a lot because this outlier is pushing it to think that the overall variation is much greater than it really is. And finally, even if your r value is really big, so really close to 1 or -1, you can never assume causation between the variables. So there's a concept here called lurking variables, and it's essentially when you have your x and y variable that look like they have a really big relationship, but in reality they're both being driven by another variable that isn't in the scatter plot. You can think of it like this: when we're looking at country demographics and statistics, you can see that number of TVs per household and life expectancy tend to have a strong relationship. So the more TVs in a household, the higher the life expectancy that you'll see in a country. And so this doesn't mean that if you want to live longer, you just buy a lot of TVs. This is actually being driven by the technological advancement of a country. So that would be our lurking variable here. What it's basically doing is, as a country gets more technologically advanced, they develop better medicine, they have a higher standard of living, and therefore people's life expectancies go up. At the same time, living conditions will improve and people will likely be able to be more economically successful, which allows them to buy more TVs. So you can see here, our TV variable and our life expectancy variable are related, but they're not being driven by each other. So TVs are not causing a higher life expectancy. Another good example of this that I like a lot is that there's actually quite a strong relationship between number of Nicolas Cage movies and helicopter crashes per year. So just something to think about. So finally, we get to our line of best fit. So this is written as, if you put it in mathematical symbols, y hat is equal to a plus bx. So a is our y-intercept and b is our slope. We were probably used to the slope-intercept form, so y equals mx plus b. Stats flips it on you, so your slope comes as the second term and your y-intercept comes first. This is again something you can get from your calculator, and this is something I will explain in my video on how to use a graphing calculator for statistics. So one thing that you'll have to do is interpret the LSRL. So the way you do this is separately interpret the slope and the y-intercept. So starting with the slope, let's say our b, so our slope this time, is 3, and we're talking about temperature and ice cream sales. Our model's slope of 3 implies that for every 1 unit increase in temperature, so 1 degree increase in temperature, there is approximately a $3 increase in ice cream sales on average. So first you'll notice that I included units. I said dollars here to include context, and then I replaced explanatory variable and response variable with more context. And finally, you'll see on average and approximately. This is basically saying that not every data point follows this trend. This is just what appears to be happening. So I said approximately and on average. This is not always true. Finally, we have our y-intercept. So let's say it is -2. So the y-intercept of -2 implies that when the temperature is 0, the response variable, so the ice cream sales, is -$2. So now that we've said what it is, we also need to comment on whether or not the y-intercept is realistic. Because right now we're making a prediction. This isn't necessarily true for all points. So that is why we need to comment on it. So you have to say this is or is not realistic because, in this case, this is not realistic because you cannot have negative money unless you are in debt. So there's some extra properties of the LSRL. Your slope, so B, is equal to, if I write it in math terms, R times SY over SX. These subscripts do not mean multiplication or anything, it's just an extra note on what the S stands for. So our B is equal to our correlation coefficient times the standard deviation of the Y variables over the standard deviation of the X variables. Another thing is that the LSRL will always pass through X bar and Y bar. So if you'll remember, X bar is equal to the mean of the X values, and then Y bar is equal to the mean of the Y values. So no matter what, your LSRL will always pass through this point. Now we have a concept called the residuals, and what this tells you is how far off your predictions are from the actual data points. So for each data point, if we draw it out in a scatter plot, if we have our LSRL here and our scatter plot looks like this, each data point will have a residual and it's equal to this distance right here. So the distance from the point to the line. Coming over here to this point, it would be equal to this distance. The way you calculate the residual is equal to the value of your data point, so your observed data, minus your expected data, so what you get from the line. If you plug your X value from the data point into the LSRL equation, then you will get the expected value. And then you subtract the Y value of the data point from the Y value of what you got from your LSRL equation. You also need to learn how to interpret a residual. So what you need to know is that if your residual is greater than 0, that means that your model underestimated the value of the data point. And if your residual is negative, that means that the model overestimated the value of your data points. And I did not write this, but if it is equal to 0, that means that your model was spot on. So now that you've taken a residual for every single point in the graph, you can actually plot these in a different scatter plot. That's what these look like. This symbolizes the value of the LSRL, and these show how far off each point was. So this point over here was about 10 units away from the LSRL. So when you look at residual plots, there's one main thing that you need to look for. It is that residual plots should never show a pattern. They should look like some random distribution. So if you look at these, this model has a clear curve to it. You can see some kind of pattern. That means that this plot is not good. So that means our model in the scatter plot that we got this residual plot from is likely not linear. And that means that we shouldn't be using a straight LSRL for this data set. It's the same thing for this one. This one looks okay, there's no clear curves to it, but you'll notice that over here, the residuals are packed really close to 0, but then as you move outwards from X, the residuals also move outwards. So this is called fanning. And this is also a bad sign. It tells you that your model is appropriate for only part of your data set, and then as you move outwards, your model becomes less and less accurate. So that means a linear model is also not appropriate for data set number 3. Data set number 1, it does look like there's a little bit of fanning here, but it is by far, out of these 3, the best residual plot. So you want something that just looks like there's an even and random distribution of points. You don't want to see any pattern, which is kind of counterintuitive. So a lot of the times you'll see a question like, is the linear model appropriate for this data set? There are 4 conditions that you need to satisfy in order to deem that a linear model is good for the data set. The first one is that both variables have to be quantitative, so both of them are numbers that can be measured. Next, we have to look at the residual plot. So whenever you're showing work here, you have to personally draw out the residual plot and then say it shows no obvious pattern. Next, you have to confirm that there are no outliers, and then the R value has to be somewhat strong or moderate. if you have an R value of 0.0001, a linear model will likely not work. There is another term called extrapolation, and that is when you're taking your model and you're predicting beyond the data set. So if we have a scatter plot that looks like this, and our data points are all over here, and we've made an LSRL based on it, if we're trying to make a prediction all the way out here, we don't know if it's accurate because we don't have actual data to back this up. So this is called we're extrapolating from the data set. So to the right here, I have an example of when extrapolation can be super inaccurate and dangerous. So we have a scatter plot of the relationship between the minutes after cardiac arrest that someone receives treatment and then their survival rate. So you can see here that the bulk of the data points, the bulk of the dots are over here. However, we have a line of best fit that runs technically on forever. So if we wanted to predict the survival rate of people with cardiac arrest after X number of minutes, but we're predicting out here. So if we extend our line of best fit, that would be about over here on the line. You can see that the survival rate here is negative, and that isn't possible. So that is where we get a really inaccurate and unrepresentative prediction from our model. This goes to show you that extrapolation can be really inaccurate and dangerous once you go beyond your main data set. One main place where we use extrapolation is when we do the y-intercept of our LSRL, and because it's extrapolation, we need to acknowledge that it is sometimes inaccurate, and that is why we always comment on whether or not the y-intercept is realistic when we interpret the LSRL. Next, a quick thing on outliers. The thing with outliers is that you can't just ignore them to make your data work. You need to acknowledge your outliers and then explain why they are there, or find some way to interpret them and how they are affecting your graph. There's two main descriptors you can use with outliers, and those are leverage and influence. You can also think of this in terms of your door. If you open the door from the place where the doorknob is, it's very easy. But if you go closer to the hinge, then you need to apply more force to get the door to move. So that is what leverage is. Leverage is where a point is very far away from the rest of the dataset in terms of its X value, and therefore it has a very strong influence on the LSRL. It pulls the most weight in terms of how much it affects the LSRL. An influential point is another type of outlier where if you took away that point from your dataset, then your LSRL would suddenly look very different. So we have 3 examples here. Each of our outliers is marked with an X, and you can see that the first scatter plot here shows a point with very high leverage. So you can see here's our main data set, and then this is our outlier. So the bulk of the X values of the points are over here, but we suddenly have a point that's out here. So because its X value is so far away, it has high leverage. We also need to check to see if it has influence. So if we take this point away, is the graph going to look any different? With this point here, let's make an estimate for where the LSRL is. I'd say our line of best fit just looks something like this. Now let's pretend that the outlier over here does not exist. So now our graph looks like this. And what does our LSRL look like? Well, the data points tend to trend upwards this way. So I would say it looks about the same with or without the outlier. Therefore, this point does not have much influence, but it does carry a lot of leverage. So leverage you can think of as potential, and then influence is that it has already used its potential. Coming over to scatterplot number 3, this is a point with a lot of influence, but not leverage. You can see that most of the data points fall around this area, and so their X values mostly range from here to here. Our outlier is right next to our set of X values, so because its X value is not far away from the rest of the data points, it is not considered a point with a lot of leverage, because only its Y value is far away, not the X value. However, it does have a lot of influence, and this is why. So let's put in our LSRL right now. I'd say it would look something like this, because it's being dragged down by our outlier. And now let's take away that outlier. So our graph changes to something like this. What does our LSRL look like now? Because all the points are up here and they're kind of amorphous, I would just put a line through here. So our other LSRL looks something like this, and then once we took away the outlier, it moved upwards so much. So that means this point had a lot of influence on the LSRL. And finally, we have our middle scatter plot. So here's our outlier. And then the first thing you notice is that its x value is definitely far, far away from the other data points. So it definitely has leverage. And for influence, if we include the outlier, our LSRL looks like this. If we pretend that it's not here anymore, our LSRL is still negative, but it is quite a big difference. So therefore, this one also shows influence. That's actually everything on scatter plots and linear regression for now. So thanks for watching. Hope you learned something. Peace.